Thanks a lot for the introduction. So my name is Marta. I'm a junior scientist and I'm working at the European Synchrotron Radiation Facility in France. And in my presentation today, I would like to focus on, let's say, why someone would like to go to a synchrotron rather than do a measurement in the X-ray diffractogram or in the X-ray or in the laboratory-based diffractogram. So my focus is X-ray diffraction. I'm part of the, let's say, LEAPS network, so the League of European-based accelerator photon sources, so not only synchrotrons, but also free electron lasers. And in this network, we offer different techniques. Of course, they're X-ray based, so we have imaging, tomography, spectroscopy, and X-ray diffraction and small angle and wide angle X-ray scattering, which somehow they overlap a bit, but with a bit of differences between them. And I will show that a bit later because my focus is on diffraction. But diffraction is part of the X-ray scattering. How does it work? We have the incident beam, so our X-rays, synchrotron X-rays, they interact with the sample and we record the change of angle between the incident angle and the interaction with the sample. This change of angle can be a small change, so we are looking at small angle X-ray scattering, which give us information about, let's say, big objects, because we are looking at the reciprocal space. In this case, big objects means nanoscale objects, so it's all relative, but relatively big objects. While when we look at the wide angle, so wide angle X-ray scattering, then we look at small objects in reciprocal space. So it's wide angle, so large objects in reciprocal space, so small object in real space, which are the atomic scale structure. So what we can do is we can look at the Bragg peak that are formed, so these intense reflections, which give us information about the crystalline phases. For example, we can distinguish what is our active material. We can see if it's copper or copper oxide, depending on where the peaks appear, so where in the reciprocal space appear. But we can also look at different phases appearing during a reaction. So we can distinguish if we are looking at a carbonate or a bicarbonate just by looking at where the new peaks appear. And then as a, let's say, plus, when you go to a synchrotron, you get more information. For example, you can look at the background, you can look at water movement in an electrochemical cell, for example. These information are not available when you look at data which are collected in a laboratory XRD, simply because of the intensity of the beam. So there's not enough photons to distinguish noise from background. And then, as I mentioned, we can also look at nanometer objects. So we can see we can look at this shoulder, depending on if, for example, it's shifting, then the object, for example, nanoparticle might be shrinking, might be swelling. We can look at the intensity to see if the nanoparticle is dissolving, for example, and so on. So we get a lot of information about the structure of the materials. To give a bit more information about diffraction, we can simply look at the position of the peaks in the diffractogram, and this gives us information about the phase. So we can just look at the position and say, okay, we have this phase, we don't have that phase. This phase is converting to that other phase, and so on. But then we can look a bit more into details. We can do, for example, Rietveld refinement. This gives us quantitative information. In this case, we are looking, for example, at the relative phase quantities. We are looking at strain, microstrain. So, for example, if the structure is distorted because of reaction occurring or other things that can happen during the sample measurement. We can look at the crystallite size. We can look at orientation, anisotropy. This is particularly if we have a 2D detector, which is very common in a synchrotron, a bit less common in a laboratory X-ray diffractogram. So all this information are available. We will just, depending on the investigation or the measurement or the investigation, depending on what you want to look at, we'll target a different instrument, we target a different beamline, a different facility, in order to tailor the data acquisition, basically. Why is interesting to go to a synchrotron compared to do a measurement in the lab XRD is because a synchrotron can do measurement harder, better, faster, and stronger, basically. If we compare the brilliance, which is a parameter which basically defines, let's say, how many photons, in short, is how many photons your sample is seeing. When we look at the laboratory-based diffractograms, we are in the order of 10 to the 7, 10 to the 9 in brilliance, which is 15 times lower compared to fourth generation synchrotron. Third generation synchrotrons are very common. Now we are seeing like upgrades. The first one was Max 4 to become the fourth generation synchrotron. ESRF recently was upgraded to the first high energy fourth generation synchrotron, and other synchrotrons are following. So we are gaining in brilliance. So we are getting, let's say, more and more samples, which allows us to see things better, basically. So these are two diffractograms. This black one has been taken on a lab XRD, a lab instrument. The red one has been taken several years ago on a third generation synchrotron. So we see the differences. This is a complex sample. It has like different compounds inside, different phases. But what we can see, for example, here in the lab XRD, we have a shoulder, but we cannot distinguish the different peaks. When we go to a synchrotron, then we have a better resolution in reciprocal space, which allows us to distinguish all the different peaks and then to do the identification of the phases. We also have a better signal-to-noise ratio. So here we see that there might be something, but it's really hidden in the background. It's very hard to see if there's a peak or not. But when we go to synchrotron, the noise is much lower, so we can really distinguish even minor impurities, minor phases, and so on. We have better signal-to-noise ratio. And then we can also have shorter acquisition time. So to acquire this diffractogram, it took 3 hours. It took 1 hour, and it can be done even faster depending on the facility. So we can really go like sub-second acquisition, which allows to do time-resolved measurements and so on. So in general, it's faster acquisition, which is also interesting if you are a company, for example, and you need to screen hundreds or thousands of powders, and then in that case, acquiring in sub-second or acquiring in hours really makes a difference. Just a bit of discussion about the energy and the resolution in reciprocal space, because they are kind of linked. So when you go to a synchrotron, you usually want to have high energy. Why do you want to have high energy? And what is high energy? When we talk about high energy in a synchrotron, we talk about 50, 60, 80, 90, 120 kiloelectron volt. So we're talking about high energy, which allows us to measure real samples, big samples, heavy samples, or samples containing heavy atoms, because we can still get a very good transmission, even if we have big objects, if we have metals, and so on. That's the problem of a laboratory X-ray diffractogram. We might not be able to measure real objects because the transmission of the beam is not enough to collect the signal. So we can measure big and realistic samples. The drawback is that we lose a bit in resolution in reciprocal space. So the resolution is proportional to the energy, or like if you want to have like a lower resolution, you need to have lower energy. And that's why it's a bit, let's say, compromise. If you want to have high resolution in reciprocal space, then you lose a bit in energy. So you go rather to beamlines which are working around 30 kiloelectron volt. If you want to measure like a thick piece of metal, then you would have to go to higher energy, like 95, 120 kiloelectron volt, and you lose a bit in resolution in reciprocal space. And that's a bit the drawback, but again, we have a lot of facilities, there are a lot of beamlines, a lot of instruments. So depending on what you want to measure, we can target a different instrument. And this has been done in the past couple of years. We measured plenty of samples. We did plenty of measurements, operando investigations on really different topics, from how to make batteries containing better materials, how to recycle the batteries, how to recover the transition metal, how to convert or how to improve the conversion of CO2 into valuable chemicals, cement from recycled concrete. So can we recycle the concrete so that we have cement with less CO2 emission? How can we create alloys with recycled materials or with high entropy alloys, which again are easier to recycle. They are potentially coming from recycled sources and so on. So it's really like diverse fields that are coming to remade to use X-ray diffraction. I will just give a brief introduction of why we need batteries, because that's my topic, that's my background, so I like to talk about batteries. I mean, I think we all know why we need batteries. I mean, in the past 15 years, we saw an increase of demand of batteries of 1000%, which is a huge increase. And is not only because of electric vehicles, because we want to reduce the local pollution, but we also see an increase due to stationary storage. So the idea is to couple battery to renewable energy sources. So we have our solar panel, we have our renewable energy source, we couple it to a battery so that we can store the energy and use it, for example, during the night when we don't have sun. So this is very important. So we cannot, let's say, escape from the use of batteries, but we are getting to a point in which the demand of the materials, the raw materials, specifically lithium carbonate, is going to, it cannot follow the demand. So the supply chain is not enough to fulfill the demand that we are seeing. And this is going to happen very soon. There are, however, other sources of lithium carbonate or like lithium, which comes from batteries that we already have. So the batteries that we have are soon reaching the end of life, especially from electric vehicles. They last 15, 20 years. So we start to see the first electric vehicles batteries reaching the end of life. And this contains a lot of very valuable raw materials, not only lithium, but also transition metal, nickel, manganese, cobalt. So all of these very valuable elements, it would be very interesting to recycle them so that we also have them, let's say, locally sourced from our cities. We also have alternatives. So instead of using lithium, which is scarce, we can use different ions for our batteries. For example, sodium ion. This is very promising. There are already the first batteries, the first sodium ion batteries, which are being commercialized. And one of the advantages of sodium ion batteries, well, first, sodium is much cheaper. It can be sourced basically anywhere, while lithium has a bit limited geographical location where it can be sourced. But also it has the advantage that we are not using graphite. Graphite is the anode of choice for lithium-ion batteries. In sodium-ion battery, graphite doesn't work, which is excellent news for us because we can use hard carbon. Hard carbon is a sort of disordered carbon, which can be produced by plant-derived biomasses. So you can use basically any scrap biomass, you burn it, you carbonize it, and you produce hard carbon. And then depending on how you are preparing it, what is your synthesis recipe, you can have hard carbon with different properties, but then you can use this hard carbon as anode material in sodium-ion batteries. So that's like a much more sustainable battery which we can produce. And then if you look in literature, depending on like where you're doing your research, you might be producing hard carbon from coconut shells or from wood scrap, or if you come from Grenoble, you want to make hard carbon from waste walnut shells. In Grenoble, we have a lot of walnut shells. We have a lot of walnuts, so a lot of shells, and we want to use them. And this is what we did with this project that we started recently. I supervised a student, Freya, who worked on this project. So we started by looking at how the structure evolved during the synthesis process. So we have a nice furnace which can get to 900 degrees. We have the walnut shells in powder in the capillary. We have the X-ray beam that is coming from this side, and then we can just look how the in this case is the wide-angle X-ray scattering, but how the diffraction is evolving during the synthesis process. We applied also to remade because we cannot do much with only the scattering techniques. We also need to know the morphology of our particles. We need to know the porosity inside the produced hard carbon. We need to know the chemical or like the chemistry of the walnut shells of the hard carbon. So we got the support from Remade at ARI to get also different techniques. This is the first part of the project. What is like, let's say, the long-term plan is you have your hard carbon done with different recipe from different sources and so on, and you want to put it in a cell, in a sodium-ion battery, and you want to see how it gets sodiated. So if it's working, you might have different structure depending on the different synthesis route, and you get different electrochemical performances. So that's a bit like the long-term project. So okay, we might have alternative to lithium-ion batteries, but we still have the lithium-ion batteries, which are, well, they are very useful for first of all, but also they are reaching the end of life. So what do we do with used batteries? So this is a project from a group that approached Remade at ARI because they're like, okay, we have our used lithium-ion batteries, our used electronics. They contain a lot of metals. We want to recover them. So what happens, for example, to lithium-ion batteries, usually you discharge them so that they are safe to handle. You crush them. You make like this powder. It's called black mass. It contains a lot of valuable elements, lithium, copper, aluminium, cobalt, manganese, like all these metals that you want to recover. And this group is using like some sort of solvent to dissolve the transition metal, and then they need to recover them. So they approached Remade asking, okay, can we get a better insights on how the transition metal are dissolving? So what is the time frame? What is the process that is happening? And for that, they asked for different techniques, among which in situ and ex situ X-ray diffraction. So I will focus on this part, on the X-ray diffraction. So this is the setup. You have the X-ray beam coming here. Here you have your black mass, so your powder that you want to dissolve. And then we have a pump so that we can just inject the solvent, and then we can look in with a time resolution. We can look how the powder is being dissolved. So this is the case of synthetic black mass. So it's a mixture of the active material of the battery, so lithium cobalt oxide, and the current collectors, aluminium and copper. And then what we saw is that in the case, if we look at the peak, which is associated to the active material, so the lithium cobalt oxide, we see a shift during this process, especially when we are below 1.5 in pH. This shift is associated to the leaching of lithium. So we are dissolving lithium from this powder. However, when we look at other peaks, for example, this one, which is associated to copper, then we don't see any change in shape, in intensity, and so on, which means that we are selectively dissolving lithium. So we are removing lithium from the powder. So we have lithium now in solution. Okay, now we are happy. We have like only one element or multiple elements in the solution. So here comes a different group, which is starting from this step. We have our transition metal in a solution. How can we recover them? In this case, they use a pump ion method in which they are recovering the transition metal with electrochemistry. So they use Prussian blue analogues, which is a material, is a structure, which depending on how it's synthesized, it contains different vacancies. So their idea is that depending on how the Prussian blue analog is synthesized, they can selectively recover only a different transition metal. So depending on the Prussian blue analog, depending on the potential that they are using, they might be able to recover only given transition metal. So again, this is the setup. We have the X-ray beam coming here. This is like electrochemical system. So we use the coin cells. These are very common in batteries, but they're used as electrochemical cells, basically. And then here we have the 2D detectors. And then what we see is that in a solution that is containing nickel, we see the shift of the Prussian blue analog, which is associated to an incorporation of nickel in the structure of the Prussian blue analog. When we do the same experiment with a solution which contains cobalt, however, we don't see the same shift. So with this Prussian blue analog, we are able to incorporate only nickel, and cobalt remains in solution. So we can now recover only one of the transition metal. So perfect, we have solved the problem of recovering transition metal from batteries. But what about increasing the lifetime of batteries so that we don't have to recycle them after 10 or 15 years, but after maybe 15, 20, or 25 years? That's a different use case. In this case, the group approached us because they are synthesizing lithium-rich layered oxides. These are very promising cathode material for lithium-ion batteries, which have the advantage of being cobalt-free. So why cobalt is so important in lithium-ion batteries is because it's stabilizing the structure so that it lasts longer. However, this group said, okay, we don't want to use cobalt. So instead of cobalt, we introduce iron in our structure, and we'll try to stabilize the structure of the lithium-rich layered oxide with iron. In this way, we'll still have long-lasting batteries. So they approached us for the X-ray diffraction part. First of all, they just looked at the whole diffractogram. They were happy because you cannot see new phases, so it means that the synthesis is successful. They are maintaining the precursor structure, but then they did some more accurate analysis with Rietveld refinement, in which they can see the defects that are forming inside the different structure depending on the synthesis route. And then they coupled this measurement with TM, transmission electron microscope, in which they can look, for example, at defects forming on the surface, and also positron annihilation spectroscopy, which give them, again, information about defects which might be formed during synthesis. So now we have like long-lasting batteries, we know how to recover them, but what happens to these materials when we put them in a battery? We might have, for example, composite electrodes. These are electrodes, so are part of the battery, which might be a mixture of different active material. In this case, is graphite and silicon. So these enhance, again, like the capacity. So your phone, instead of lasting 12 hours, is lasting 24 hours. So with this experiment, we can look at how the inhomogeneities in these batteries are propagating, or how they are present inside an electrode. So we can look at different height in the electrode. So if you have a thick electrode, we can look at different slices. We can look at how the inhomogeneities are present at the different height. And in fact, what we discovered is that at intermediate lithiation states, the lithiation of graphite and silicon is very inhomogeneous. The homogeneity comes only when we are fully lithiated. So what does it mean is that we have part of the battery, part of the electrodes that are overworking, and parts of the electrode that are underworking. So we are putting more stress only on some part of the battery, but on average, the stress is the same. So what it means is that your battery, instead of lasting 5 years, it lasts 2 years, because part of the battery are just dying earlier than expected. We can also do a lot of other experiments, just like to give an overview, we can do like synthesis, catalysis. So we have like in many different synchrotrons, in many different beamlines, there are this kind of capillary cells. So this one, for example, comes from the Swiss light source, but it has been used in ALBA, it has been used in DAISY, it has been used at ESRF. So it's a portable, I would say, setup. So you have the capillary inside, you can have gas flow, you can have different temperature, and you can basically follow changes that are occurring on your material in situ, doing changes in gas flow, for example. So depending on how much pressure you're putting on the capillary, you can change the temperature, you can look at evolution in time, and you can look, for example, at the appearance of different peaks. You can see how different phases are disappearing and so on. And if you want to learn more about catalysis, especially, my colleague from the Smart Science cluster, Aram Bugayev, already gave a presentation, so you can find it on YouTube and you can learn more about catalysis, especially in situ measurements. So I'm approaching the end of my presentation. I wanted to give an overview of what you can do in a synchrotron that you cannot really do in a laboratory scale instrument because of the higher flux, the higher brilliance, the faster experiments, the higher energy, and so on. So basically, you can use different scattering techniques. In this presentation, I focused on the X-ray diffraction, so looking at the peak evolution, let's say. But you can also combine it with different techniques that gives you more information about local structure, like per distribution function analysis. You can look at nanoscale objects with small angle X-ray scattering and so on. X-ray diffraction is particularly useful in circular economy because you can look at we have plenty of examples. We can look at in situ and operando measurements. So you can look at how your metals are being recovered in real time. You can look at the charge transfer, so how your material is evolving during, like you take your recovered electrode and you can look at how it lithiate or sodiate in real time. You can look at more sustainable compounds. So for example, these lithium-rich cobalt-free cathodes, but also like you can look at sodium-ion batteries, and then you can look at fast reactions in catalysis, in synthesis, and so on. Before ending this presentation, I would like to bring your attention to a few things. First of all, we have the catalog of techniques online, which is a collection of all the techniques that are available within the remade ATARI projects. So you can have a look just to get an idea of what we can provide. And then you can apply if you're interested. We can, Mary already talked about this pre-proposal process. So if you are interested, but you don't know which technique you can use, you can just approach us and we will help you to find the best technique that will answer your question. And then we have the next call for, especially for academic, but not only, so the transnational access, which opens at the end of August. And we have the small and medium enterprises call, which ends in April. So get in touch with us and we'll help you to find which call is more suitable for you, which techniques are more suitable for you. And at ESRF, we will be hosting in September a conference, the Multi-Probe Imaging for Materials, in which you will learn more about tomography and imaging, not only using X-ray probe, but also using, for example, electrons or ions. So you will learn more about all these techniques. And we are accepting abstracts so until the end of August. So before going on holiday, don't forget to submit your abstract for this conference. And thank you very much for your attention.